Alright, so in this video we go over chapter 2, displaying data, and in this case we are going to look at the different ways we can display data in the form of graphs and in some cases tables and some properties here and there. So in this case, to make this video shorter, this is going to be more like a presentation. All the calculations are already done. I'm just going to explain how the calculations are done, which is really simple calculations, very basic operations. All right, let's define first of all frequency distribution. So a frequency distribution is a two-column table in which in the left column we list each value in the data set from least to greatest, and in the second table we count the number of times each value appears in the data set. Let's look at a very brief example. So the data set right here represents the daily demand of SUVs sold at a car dealer over the last 20 days. Let's develop a frequency distribution to summarize this data. So if you observe the numbers, well, the numbers oscillate between 0 and the largest number is 4. So in this case, we can simply draw write a column. Right in the column, all in the x the number, the value in the data set. For example, we are going to list how many zeros do we have, how many ones do we have, how many twos are we going to have, how many threes, and how many fours. So in this case, well, I have tallied all of them using different colors and shapes. For example, how many zeros do we have? So we're going to look at the table and look at the number of zeros that I have done with this triangle here, with this purple triangle. So I have 1, 2, 3, and 4 zeros. So I'm going to count 4 zeros. How many ones do I have? Well, it looks like there's only 2 ones, and let's write that down. How many twos? Well, the twos are in green circles, so that's 1, 2, 3, 4, 5, 6, 7. Write down that 7. How many threes? We have 4 threes, which are tallied with red X's. So we have 1, 2, 3, and 4. List them here. And finally, how many fours do we have? Well, we have 3 fours, and in this case those are the three orange squares, 1, 2, and 3. So we need to find the total. Well, we don't have to add them because, well, they're telling us in the text in the problem that we have 20 observations. So once we have the frequency, that is all the counts, we are going to find the relative frequency, which in this case is frequency divided by the total. That's how we find the relative frequency. For example, the relative frequency for the zeros, that is no SUV sold, well, that's 4 divided by 20, that's 0.2. Relative frequency for ones, that's in this case the frequency divided by the total, that's 0.1. And then the relative frequency for twos, whatever the frequency is, which in this case is 7, divided by the total, which is 20, we get 0.35. The number of threes, which is 4 total, divided by the total, well, we already did that, that's 0.2. And last but not least, the number of fours, which is 3 divided by 20, in this case 0.15. And you might want to think of relative frequency as, in a way, gateway to take us to percentages, if you will, because, for example, this, if you wanted to represent as a percent, this 0.2 represents 20%, this 0.1 represents 10%, this 0.35 represents 35%, this 0.2 represents again 20%, and this 0.15 represents 15%. All right. So depending on the problem for relative frequency, you might be asked to record those results as percentages or sometimes as decimals. We will look at the decimals in order to find the cumulative relative frequency. The cumulative relative frequency, well, we start with the first one, we just copy it down. And then to get the relative frequency for the next step, what we do is add the previous one with the next one. In other words, we add this to the 0.2 and the 0.1 to give us a 0.3. So we are accumulating the first class and the second class. All right, by the way, these are called classes. Each label on the observations is one class, another class, class. And then for the third cumulative frequency, we add the total of the previous two frequencies, relative frequencies, and that of the third. In other words, 0.2 plus 0.1 plus 0.35, 0.65, and then we keep going with the fourth class, the total from the previous one plus the one on the current row or in the current class, and that's 0.85, and finally we add the last one and we have to get a 1. So to verify that your work is correct, well, the relative frequency has to give you always a 1, or which in percentage means 100%. And the cumulative relative frequency, they always have to add up to 1 as well. Or sometimes, depending on the rounding, I mean, you might want to be very careful with the rounding. Sometimes you could get 0.999 or 0.98, something like that. Okay, so this is a very simple case of frequency distribution. But what about when we have too many outcomes? For example, the data set below right here represents the number of calls per day made from a cell phone for the past 30 days. All right, number of calls per day, for example, the first day of the month and then the last day of the month. Let's say we are in April, for example, which has 30 days. All right. So on the first day, 4 calls, 5 calls, 1 call, no calls, 7 calls, 12 calls, 14 calls. Well, in this case, it worked okay to group the data into classes like 0, 1, 2, 3, and 4. But what if we have like more outcomes? Like in this case, we have outcomes from 0 to 14. In that case, it's not efficient to rather represent the data using 14 classes. So no, it's too much. So what we do in this case is group the data into classes. All right, into classes with ranges each. For example, what we're going to do in this case, in classes that have a size of 3 each, and in this case, so what do we mean by a class that has 6 that has a class size of 3 each? So in this case, I'm going to start with the lowest outcome. So the fact that the size of the class is 3, it means that if I start with 0, that's the first in the class, 2, 3. Well, 0, 1, and 2, that's 3 elements. Or way even better, if the first class starts at 0, add 3 to get the lower bound of the class. Actually, by the way, these two numbers, the 0 and the 2, are the bounds of the class. This is the lower bound and this is the upper bound. What you can do is start with the class with the lowest number, add the size of the class or the class width. That's another way of calling this. Class width. Add 3 to get 3, and then add 3 to get 6, and then add 3 to get 9, add 3 to get 12 rather. And notice the very last upper bound is the highest of the outcomes here. If we had, for example, a 16 or a 17, then we would need another class to group that data. And then what are we going to do? Well, this time, instead of looking for only zeros and have their own class, we're going to look for all zeros, ones, and twos. And in this case, well, for the zeros, ones, and twos, I tallied this using this purple triangle. So I have okay, looking at every single row, look for ones, zeros, and twos, or zeros, ones, and twos. So I have a 1, I have a 0, there's a 0 here, and then there's a 2 here, there's another 2 here, there's another 1. So if we count them all, there's a total of 6, which is the 6 right here. Now we're going to look for the entries that are 3s, 4s, and 5s. For those, I use the green square. So 4s, 5s, and 3s. So I have 1, 2, we're done, 3, 4, 5, 6, 7, 8, 9, 10, and 11. A total of 11 observations that are between 3 and 5 inclusive. Now, what about of the observations that are between 6 and 8? Well, between 6 and 8, I use pink circles here. In this case, well, let's go with the first row. So that's 1, 2, 3, 4, nothing, 5, 6, 7. A total of 7 observations that are listed here. All right. And then from here, well, let's look at all the observations that are between 9 and 11. We have 4 total. Well, so in this case, I tallied this using orange X's. Well, nothing here. There's 1, 2, 3, and 4, right, that are listed here. And finally, all the observations that go between 12 and 14. And in this case, there's only 2, and I use this kind of magenta bubbles. There's only the 2 and the 14. There's only 2 observations. So we're going to do the same. We're going to do the relative frequency, which we're going to divide the frequency by the total. Let's write it down. Frequency divided by total. Okay. And then, well, 6 divided by 30. In this case, the total is 30. Well, they're telling us in the problem, and we list it here as well. 6 divided by 30 should get 0.200. 11 divided by 30, 0.367. 7 divided by 30, 0.233. And 4 divided by 30, 0.133. And 2 divided by 30, it's 0.067. And of course, you might want to change those to percentages because, well, depending on the homework question or the exam questions, you might be asked to report one or the other, or possibly both versions of it. And then again, for the cumulative relative frequency, well, we start with the relative frequency from the first class, and then we start adding them all up. So 0.2 plus 0.367, and then that's 567. Then add 0.233, we get 0.800. Then add 0.133, which is this value here, we get 0.93. And then finally add 0.067, which is this number, and then you should get 1. All right. So sometimes you might be required to represent the data graphically, well, with a bar or with a line, and then look at the shape of the distribution, you know. So for 0 to 2, 3 to 5, all the different classes, we are going to represent with a line or a bar that represents the frequency. That, like, this line possibly represents a 6. This one is bigger because it represents an 11. This one a little smaller because it's a 7. This one a little bit more smaller, which is 4. And the last one, it's a tiny one because the frequency representing is 2. Being represented is 2. All right. We're going to look later in the following chapter about the distributions, right? But in the meantime, we can say that this is skewed to the left. All right. What about histograms? Histograms are like bar charts. Histograms are basically frequency distributions in a bar chart. So that's how we can define a histogram. So we're going to develop a histogram for the data below that represents the grade distribution for a statistics class. And in this case, we're listing the number of A's, the number of B's, the number of C's, the number of D's, and the number of F, which in a total we have 30. So, well, in this case, we are going to do like a Cartesian plane, if you will. It's not necessarily a Cartesian plane because we're not plotting functions, you know, like in algebra, but you can think of it. So, in the X component, if you will, write down the categories, in this case, A, B, C, D, and F. And in the Y component, we are going to label the possible outcomes, which in this case is the frequencies. You know, if you look how to draw this, well, there's no right or wrong way to do this. You know, in this case, my y-axis, I did it by scaling by 2, 4, 6, 8, 10, 12. But it could have been 3, 6, 9, and 12. I mean, either way, it's correct. There's no right or wrong way to do this. So for the number of A's, well, there's 9 A's. So I'm going to draw a bar whose height is 9 units. That represents the number of A's in the class. B, the B is 12. So let's go to the B, draw a bar, and you know how a bar high enough to represent the 12. Of course, my drawing is not perfect, but you get the picture, hopefully. The number of 6, which is 6. Well, let's go to the C, draw a bar high enough to go and represent the number which is 6. The number of this, which is 2, well, so that's gonna be this one here. Finally, the number of F's, there's only one F, this tiny little bar where it corresponds for the grade F and with a height of 1 unit. Notice in this case there's gaps in between the bars, and that's because we have discrete data or categorical data. You know, if we were talking about continuous data, you know, these bars would be all together, like in the next case. I'm going to discuss the difference after explaining the next step, the next example rather. So example number 4, develop a histogram for the frequency distribution below, which is the commuting distance of 50 employees of a particular company. So in this case, well, these are grouped in classes. So the employees whose commuting miles are between 0 and 4 miles, 4 and 8, 8 and 12, 12 and 16, etc. Right? So in this case, on a particular company, 3 employees commute between 0 and 4, 10 commute between 4 and 8, 6 between 8 and 12, etc. In this case, well, because miles, you know, these 4, well, all the 0 and 4 includes not just integers, could be 3.1 or 3.75 miles, right? Remember from the previous chapter, these are continuous, 3.68 miles, 2.71, 2 miles, yes, this is an integer, but I mean, you could think it's discrete, but I mean, it's distance. A distance can have decimals. It's not like in the grades. A letter grade is just A, B, C, D, and F. There's no such thing as 8.5, right? Or 8.73. No, that's this is discrete data, and this is continuous data. So in this case, we're going to represent this again. The x-axis represents the category between 0, 4, 8, 0 and 4, 4 and 8, 8 and 12, 12 and 16, 16 and 20, 20 and 25. And because we're looking at continuous data, in this case, there's no gaps between the two bars, between each bar rather. So in this case, again, for the y component, there's no right or wrong way to label. I mean, you could do by 3 again, like 0, 3, 9, 12, 15, 18, 21, 24, you know. I mean, the maximum is 16. You could go all the way to 18, you know, if you divide by 3 each. In this case, I did division by 5, 10, 15, and 20. 20 is my largest. I cannot stop at 15 because there's a 16. I need one more label. And of course, the bars represent each frequency. So between 0 and 5, I need a 3 to represent the first frequency. The second bar is 10 units long, and then the third bar is 6 units long, and then 16 units long, or tall rather, not long, is tall, the correct term here. And then 6 again, and then finally 9. All right. So again, that's the difference between histograms with no gaps because of continuous data. You know, so let's highlight that. No gaps means continuous data. And gaps mean that we are working with discrete data. All right, let's move on to the next topic, or rather the next example. So let's develop a histogram with 6 classes for the data set below. The number of home runs hit by 40 Major League Baseball players during the 2008 season. And here's the data. We want we want this with 6 classes. Well, this formula that I didn't discuss before, we need to find the class width first. So the class width is obtained by subtracting the smallest value in the data set from the largest value in the data set. Well, so in that case, the largest value that we observe, the nice thing about this table is they're giving us the data in descending order. So this is the largest and this is the smallest. All right. So what we do is subtract 48 minus 26. Okay, 48 minus 26. And oops, no. Oh, okay, clear. 48 minus 26, and then 22, divide that by 6, and we are going to get a decimal. In this case, every time you get a decimal, to find the class width, round it up to the following integer. In this case, well, it would be 4. Even if your number is 3.1 or 3.2, I know what you might be thinking. Well, 3.1, 3.2 actually rounds down to 3, but in this, because it's less than 0.5. So in this case, for these purposes, for statistics in this particular topic, we always round up to the next integer, right? In this case, 4. That is, I'm going to start with the smallest of the observations, which is 26. Okay, 26. And the class width is 4. I'm going to add 4 to get 30. I'm going to add 4 to get 34. I'm going to add 4 to get 38, and so on and so forth until I get to the highest possible. Well, in this case, the highest upper bound is 49, even though it doesn't go all the way up, but at least it's going to cover the largest of the observations, which is 48. Which is contained in this interval, or this class rather. And then what are we going to do? Well, so I'm going to label this as each of the classes as A, B, C, D, E, and F. The number of observations that go from 26 to 29. I'm going to observe and observe and count them. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the last 29. And the next is a 31, but 31 should belong in the next class. So I'm going to use a different color to to actually label. Look at the other. So everything between 30 and 33 inclusive, so that's going to be, well, there's no 30, I'm going to go 31, 31, 32, 32, 32, 32, 32, and there's a 33, 33, 33, 33, 33, 33. So all those many. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which are recorded there. I'm going to use green to count everything between 34 and 37. So 34, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the next is 38. It's not in that class, so I have all 11. And last but not least, well, between 38 and 41, well, I only have one observation, 38. There's no 40s. Well, actually, yeah, I have two observations, 38 and 40. So those are these two observations here. All right. And let's see, what else can we do here? Well, so let's use a different color. I'm going to use purple for, well, in this case, between 42 and 45, there's none of them. There's nothing, so that's why I actually have 0. Well, yeah, the color go kind of weird. And I'm going to use purple, some shade of purple for all between 46 and 49, and the only one we have is this 48. And I'm gonna circle so the colors don't blend. All right, so below it's is the graph that represents everything in the class A as I label them. So I'm gonna highlight with the color I used. All the B's were represented with, notice these are not grades, as in these are just the category B, which A is really 26 to 29, 30 to 33, and then 34 to 37. Well, looks like the colors are gonna blend here. And then for D we have yellow here. So there's this tiny one and no bar over here. Notice the absence of a bar, and that's because there's a 0 here. There's no observations between 42 and 45. And the last bar will be, of course, that of the purple one with only one single observation. All right, let's see what else can we talk about as far as graphs or ways to represent display data. Bar charts, well, column bar charts use vertical bars to represent categorical data. The height of each bar corresponds to the value of each category. I mean, as we have doing it. So let's do more examples. But notice in this case again, it's very, very important to highlight that categorical data is also discrete data. And again, when we do these graphs have to look like this, with gaps. So it's worth noting here with gaps between each bar. All right. So in this case, what do we have? So this, let's construct we have the bar chart of the data of this data here, in which an individual's credit balance at the end of the last 8 months. So at the end of the first month is $375. At the end of the second month, $514, etc. And in this case, well, look at the numbers, at the balances. in these numbers, observe the largest of the observations. That's going to help us how to divide the y. I mean, in this case, I did by 200s each, but you could do it by 900s if you will. Notice it doesn't even get all the way to 1,000. The largest is 882, pretty much 900. I could have done 300, 600, 900, but in this case I did it to 100, 400, 600, 800, 1,000. Well, for one, that is the end of the first month, the end of the second month, the end of the third month, the end of the 8th month, I mean the end of each month, and the balance, and in this case to represent $375, well, that's this bar. The second bar represents $514. The third bar represents $834. The fourth bar represents $603. The fifth bar represents 882. That's the tallest of the bars. 468 and 775 and 585. You know, I mean, what else can we do? So these bar charts can even be done in a horizontal way. I mean, they work the same. The only thing is that we interchange the labels of the axis to draw the bars, and in this case the vertical bars is the category, and the horizontal, not bar, the vertical line or the vertical component is the categories, and the horizontal axis is the actual observations or the amounts or frequencies, if you will. All right. Well, not frequencies, it's actually amounts. Let's call it amounts. So in this case, well, we have weekly donations for a fundraiser. Well, week 1 is this money. Week 2 is all this for each week. So for the first week, 2070, well, I drew a bar that it's representing basically the 2070, which is roughly right here. And notice in this case, I looked again at the largest of the data, at the largest of the amounts in this case, which is 2412. So going all the way to 3000 was fine. And in this case, I did it by 500 each scaling. I mean, you don't want to do 100 by 100, especially because you're going all the way to 3000. That'll be a huge, that'll be overkill in the sense of, labeling and scaling. So 500 is fine. And then 2247, well, somewhere here. 1850, somewhere here. You know, the bars represent, or in this case, not the height of the bars, but rather the lengths, because they're horizontal or horizontal bars. All right. And so on for the rest of the bar. 1955. 2412, 1782. Okay, let's see what's next. So there's more about bar charts, but this is a really interesting way, grouped column bars. And in this case, we use this kind of bars when we want to compare that data from two different observations. For example, here we have the number of sales of several weeks throughout a month, I guess, because there's 4 weeks in 2 different stores. So let's say you have I don't know, you have this big company and you want to compare the amount of sales in 2 branches in a particular place, in a particular city or community. So well, in week 1, store 1 sold 502 units of a particular product, and store 2 sold 438 units of that same particular product. In this case, we're not being very specific, we're just playing with numbers. And then store 1, store 2, store 1, store 2, and then the last week, 4th week, 419, 575. So essentially what we do is label, or rather color code each store, using each store color code each store. In this case, store 1 is the green bar, store 2 is the color, the orange bar. And what we do is the same. Well, label the x-axis as the category name, week 1, week 2, week 3, and week 4. And then for the amounts, again, look for the highest of them. Well, it looks like there's like a little bit higher than 608, 600, almost 700. So in this case, I went by 200 each. But again, you might want to do, if you prefer, a 100 each. But doing 100 might be a little bit too many labels. So 200 is fine. And all we do is represent each bar, to compare, and in this case to draw conclusions, to compare the number of units sold in for that particular week for every single store, for each of the stores. For example, in the first week, it looks like, just looking at the numbers, store 1 sold more than store 2, and in the second week, store 2 sold less than store 2. And you can see that here we see it numerically, but here we see it graphically. Let's say you're working at that company and you want to present results to your boss. Well, that's what you would do as a manager. Collect data and represent it in side-by-side graphs. That's another way to call this graph grouped column bar or side-by-side bar charts. Another way to represent this kind of information when comparing, is the stacked column bar. And in this case, what we do the total. We need to find the totals. So, which in this case, we add these two numbers for each. 502 plus 438, that's 940. So we have the totals to have an idea of how high each bar combining the two, green and orange, it's going to be. For example, in the first bar for week 1, so store 1 sold 500 and, here it's kind of messy. Let's say 502 is right here, and store 2 sold an additional 438, totaling 940, which is roughly represented here. And in this case, you can see the ups and downs of each store, and also seeing the overall total of the two stores combined. So in a way, it's useful for those two purposes. All right. And again, I use 300 each in this case because when I add all the numbers, when I add all the totals, the largest value is 1245. So it wouldn't hurt to go all the way up to 1500, even though it doesn't. The largest bar doesn't reach that high, but it's okay to go all this way. Again, you could have done maybe by 200, but maybe that would have been overkill. It would have been a lot. All right, let's look at another very, very common type of graph, which in this case is pie charts. Those are very, very common, and we use this to represent in a way percentages of area of a circle based on the frequencies. For example, let's look at this one right here. Let's construct a pie chart for the data set below. In this case, the number of students who got an A, a B, a C, and a D. No F's in this case. Only A's, B's, and C's, and D's. Now, how do we construct a pie chart? So in this case, we need to find the relative frequencies. Okay. Multiply each relative frequency distribution by 360 to calculate the corresponding central angle for each category in the pie chart. So a central angle has a vertex at the center of the circle and sides that intersect the circle. So that's going to define the boundaries. So the angle, the width of the angle, it's going to define the frequency in this case. In this case, well, typically what we do is round relative frequencies to 2 decimal places for this case. All right, so we can get as close as the closest integers possible. So this is what we do. Okay, so number of students who got an A, a B, a C, and a D. Well, I just copied them again. I mean, even though they're given here. So let's find the relative frequency, which we already did in the first couple of pages. What we do, let me write it down. So frequency, the frequency that we get here, these are the frequency, divide that by the total. So 9 over 30, I get 0.30, and 12 over 30, we get 0.40, 7 over 30, we get 0.23, 2 over 30, we get 0.07, which if you want to write this down as percentages, this is 30%, this is 40%, this is 23%, and this is 7%. All right? And then we are going to find the central angle of each category. We multiply this relative frequency 0.30 by 360, 0.40 multiplied by 360, 0.23 multiplied by 360, 0.07 multiplied by 360, and these are the numbers we obtain. All right, 108 degrees, 144 degrees, 83 degrees, 25 degrees. Of course, these have to add up to 360 degrees, which is, you know, all the degrees that are inside of a circle. Okay, so let's observe this angle of 108 degrees over here that represents the first category. Okay, let me put it so everything can be seen. Yes. And I already pre-filled this for you, like I mentioned. Instead of spending too much time doing all these calculations and drawing the graphs, I'd rather just give you everything and just explain how is everything obtained. So, well, 108 degrees is this, it's this angle here, 108 degrees. And then for the B's, the area is covered by an angle of 144 degrees. And then, well, the frequency got smaller, thus there is this 83 degrees. And then finally 25 degrees. Well, the colors kind of blended here, right? Again, well, here in this sector of the circle, we have 30% of the data concentrated. For B, we have 40% of the data concentrated. And then for C's, we have 23% of the data. And finally, the number of these represents 7% of the data. And of course, all these have to add to 100. And that's how we do a pie chart. So again, in a nutshell, get all the frequencies. Most of the times you will be given the frequency, so that's a given. All you have to do is divide by the total, and then to get the relative frequencies. Once you get the relative frequencies, simply multiply by 360 to see the degrees. In some cases, you might be asked questions not about the angle, sometimes about the percentages given the graphs or given the numbers. So you might want to watch with the different kind of questions you get. Other ways to represent data called line charts. Well, these line charts are used to display data that changes over time. You know, not like in this case. Well, we're not collecting a sample at the same moment and then analyze that that data, right? So what we're doing is we get a sample from one time and then another sample from a different day or from a different year, depending on the intervals of time that you want to study all this data, right? So like in this case, well, so this is like plotting points. I mean, from very basic algebra x and plotting x's and y's. All right. So what we do is look at this graph to see how we have increasing, decreasing, or simply being held constant, there's no changes. Like in this case, well, they're asking us to construct a line chart for the data set below, in which this is the number of wins recorded by the Philadelphia Phillies for 7 seasons. That is starting in 2002 all the way to 2008. And well, we have the number of wins for every single year for the Philadelphia Phillies. 80, 86, notice it remained constant, 88, and then we have a little loss, go down to 85, up to 89, and then way up to 92. So what we do, well, label 2002, 2003, 2004, etc. And for this type of graphs, we draw a box. We draw a box in this case at not a bar, a box at a height that represents the frequencies or the total number of wins. And then in 2003 we had 86, so we're going to go up to 86, all right? And then 2004 again again 86, and then 2005 it's 88, and then a little bit down again to 88, and then 2006 is 85, and then go up to 89, keep increasing, and then finally 92 in 2008. So here, this type of graphs help whatever company is analyzing data to determine trends. Are we increasing are the Phillies in this case increasing in wins over time, or are they getting lame? Are they decreasing? Well, no, in this case, most of the times they were going up, except for this little, the little part right here. Well, they went down, but then they recovered in the following year, and then they kept going up. All right. So there's another example right here in which we would actually use negative numbers. Oh, this is the first time we're going to use negative numbers, and so far what we have in the class. So we're going to construct a line chart for the data in the table below, the percent change in annual profit for a company by year. And in this case, these type of graphs are going to help a company whether what was the highest profit and what was the lowest, well, rather the worst in terms of loss, because in this case negative percentage in profit really means loss. So in 2001 their profit was at 3.8%. So let's do about a little square right here. Oh, by the way, once we do these squares, we connect the squares by lines, which is what we're going to do over here. Well, you're seeing these lines, guys. But in 2002, the company had some trouble, I guess, had some financial, and well, technically they were in a loss, and they kept losing in the following year, in 2003. But by 2004, well, they made changes in their company and their numbers went up. They kept going up. In 2005, they went from 3 to 4%. But again, they're starting going down in terms of profit in 2006. But again, they went up in 2007. So in this case, we are using both sides of the graph. The positive to analyze the positive profit, and the one below for negative profit, that is earnings and losses. All right, so scatter plots. Scatter plots are very, very important. We're gonna look at scatter plots more like at the end of the semester when we look at chapter 10 in linear regression. So in this case, these are graph very similar to the previous, except for we don't connect each point by a line. So we're gonna do something else. So these scatter plots are used, or actually these plots show how much one variable is being affected by another. All right, and if there is a relationship, which actually we're not gonna do that in this chapter, but later in the semester. And if we're gonna collect this data, we're gonna put it in the calculator. We're gonna look at some numbers, and then from there we are going to decide whether the two variables are related to one another. And in this case, and there is a correlation. So the variables are correlated. So we have this table right here. So let's construct a scatter chart for the data in the table below. The number of hours each student studied for an exam and the scores they earned on the exam. So let's see if we're going to look at whether the number of hours studied had an impact in the exam, in the final exam score. Well, it's not a final, it's just an exam. So this is what we do. Let's label the x-axis 3 hours, 4 hours, 5 hours, 6 hours, etc., all the way to the largest amount of hours. And the scores in the exam going, in this case I started at 60 and the highest could be 100. Okay, so basically what we're doing, we're plotting points like in basic algebra. X equals 5, y equals 84. So x equals 5, y equals 84. And then x equals 7, y equals 92. X equals 7, y equals 92 right here. And then x equals 4.5, y equals 8.80, y equals 82. So 4.5, 82. And x equals 7, y equals 80. X equals 7, y equals 80. So in this case, it's very important to observe that two students actually studied 7 hours, but one of them had a 92 on the test and the other one had an 80 on the test. Well, I mean, so I guess it just by looking, I mean, by drawing conclusions, looking at the data, well, we could potentially find out that the number of hours studied does not, I mean, the score on an exam does not necessarily depend on the number of hours studied. But that's like a very rough conclusion, because I mean, just from 2 points, that's not enough evidence per se to draw such conclusions. So we need to look at a little bit more of the data, see how is distributed in this case. Well, and then we keep going, you know. X equals to 8, y equals to 90, x equals to 8, y equals to 90. So this is how we plot these points. So here in the side note, here, like I mentioned before in chapter 10, linear regression and correlation, we're going to input all these points in the calculator, and we are going to obtain the line that best fits. So in this case, we're going to draw a line. The line that is exactly like in the middle of all these points, you know. So, and then notice how some points are away from the line. That's, you know, how that's depending on how far away are all these points from the line. Well, maybe we have enough evidence here to conclude that exam grade depends on the number of hours study, or maybe not. But well, I mean, right now we're not going to do that, just showing you what scatter plots are. So we're going to get into this more in detail later in the semester. Alright, so let's do a little bit more in frequency distributions, more like technical details. So in this case, I'm going to write a little bit more. Everything else was, you know, more like a presentation. So there's a little bit more when it comes to frequency distributions, especially when we represent this using bar charts, right? In some cases, depending on our purpose, you might want to represent the graph using having gaps in between or no gaps in between. So I will show you the difference. So lower class limits, all these, we pretty much defined them already. Again, let's just recall what a lower class limit is, which is the smallest of the numbers that can belong to the different classes. And the upper class limits are the largest number that can belong to the different classes. Class boundaries, this is new, are the numbers used to separate classes but without the gaps. That's it. We're going to use class boundaries when we want to represent the graph without gaps. So we don't have to use this all the time depending on our purpose. And this is how we obtain those classes. Yeah, the long formula looks big because of the text rather. But all we do is add the upper class limit of one class plus the lower limit of the next class or the following class. Whatever you obtain, divide that by 2. Class midpoints are the midpoints of each class. They are obtained by adding the lower class limit plus the upper limit of a given class and then divide by 2. And then the class width we already defined. We also called it class size. That's the difference between 2 consecutive lower class limits or 2 consecutive lower class boundaries. So we have this example. Consider the frequency distribution below. So it's given in classes and the corresponding frequency. Alright, so identify each of the following. The lower class limits. So the lower class limits, I'm going to highlight them with pink, are the lower numbers of each class. So in this case, let's list them. That's 15, 25, 35, 45, 55, 65, and 75. All right. And let's see the upper class limits. Let me use a different color to represent this. I'm going to use yellow. So these are the upper class limits. So in this case, are going to be 24, 34, 44, 54, 64, 74, and 84. Okay. The class width. How do we get the class width again? For a class width is the difference between 2 consecutive lower class limits or 2 consecutive lower class boundaries. Right? So in this case, this is what we do. So we are going to find the difference between 2 lower class limit, like 25 minus 15, that's going to give us 10. 35 minus 25, it's also 10. 45 minus 35 is also 10. So in this case, I'm going to use 25 minus 15. That's a 10. Or you could have used 35 minus 25, or even 75 minus 65. Either one you choose is fine. You should get the same value for each. Class midpoints. Okay, so for the class midpoints, we're going to find the number that lies exactly in between each class. So in this case, what we're going to do, so class midpoints, let's go back. Lower class limit plus upper class limit of the same class and then divide by 2. For example, I'm going to calculate the midpoint, the class midpoint of the first class, and we do that by 15 plus 24 and then divide by 2, and we get 19.5. So 19.5 is the number that lies here. Well, I can't write it, but 19.5 is exactly it's the midpoint of this first class. And then for the class midpoint of the second class, we do 25 plus 34 and then divide that by 2. What are we going to get? 29.5. Now, if you don't want to do all those calculations, what you can do, because I mean it could be a little bit tedious to do this number plus that number, enter, divide by 2, enter, boom. That might take a while. Well, all you can do is simply add the class width. That is add 10, so that's 39.5, 49.5, and 59.5, 69.5, and then there's one more 79.5. Of course, we're not going to go 89 because we don't have that class, all right? So you can do that. Class boundaries, be careful with those ones. So for example, in this case, class boundaries are obtained the upper class limit of one class plus the lower class limit of the next class. That is, let me look for a good color. Okay. Upper class or upper bound of upper class limit or upper bound of one class plus lower bound of the next. Add these two, divide by 2. Okay, so this is what we're going to do. 24 plus 25, 49, divide by 2, 24.5. That is the midpoint between the upper class of a class and the lower, or and the upper bound of a class and the lower bound of the next class. So the number is 24.5, but I'm gonna leave a space here. 24.5. I'm gonna leave this space for a reason. That is, between these two classes there's a 24.5. Do you want to do the next one? Okay, let's do 34 plus 35 and divide by 2. 34 plus 35, divide by 2. We get 34.5. 34.5. Okay. But again, you don't want to do all these calculations all the time. Do you see that the difference between each class boundaries is the same as the class width, that is then 10 units. So just add 10 units to all of this. So that's going to be 44.5, 54.5, 64.5, and 74.5. All right, this is where the 74.5 is. Now the problem here in this case, we need to go one more for each. So for the highest that we calculate, do one more. That is, add 10 to this to get 84.5. And over here we need a boundary, a lower boundary right here. So we do one more, less than the smallest. So in this case, subtract 10 to get 10, or actually 14.5. All right, so that's why I left this space in blank to fill in those numbers. So those are the class boundaries. The number of individuals included in the summary, well, all we have to do is find the total. So let's add 30 plus 32 plus 16 plus 3 plus 6 plus 1 plus 1. We get 89. And this is it. Now, how are we going to use class boundaries, class midpoints? What are the representations in graphs? All right. So depending on how you want to display this data, do you want to represent class class limits with gaps, or do you want your graph with gaps or without gaps? So if you want to represent your data graphically with gaps, we use class limits. Otherwise, if you don't want gaps, you use class boundaries. So in this case, class limits. So the first class belongs to the 15 to 24, as it is stated here, 15 to 24. The second class represents 25 to 34. Here it is, 25 to 34. And then 35 to 44, 35 to 34. 45 to 50, 45 to 54, and 45 to 54, etc. Notice in this case, there's gaps in between because in this gap, we have all the 24.1, 24.2, 24.3, or 24.111, you know, all those numbers that are not between 24 and 25. Now, if you don't want gaps otherwise, then you have to use the class boundaries. And we start with 14.5, and then this one is 24.5, and then this is 34.5, 44.5, 54.5, 64.5, 74.5, and 84.5. These numbers are where these two bars are together. All right. So again, it depends. What do you want? Do you want to display data with gaps? Use class limits. Do you want the data with no gaps? Use class boundaries. How to calculate them? Here's the formulas. Here is how. Here is an example of how to do it in either case. And to wrap up this video, so you are gonna look at what's this called? At problems like this. You know, you're gonna be given a data set, and then draw a frequency distribution in which, well, we are given 25 home voltage measurements, and they want us to do 5 classes, beginning with a lower class limit of 118.6 with a class width of 0.2. All right, so this is what we are going to do. I'm going to start with 118.6, and then the class width will be 0.2. That is, I'm going to add 0.2. And let 118.6 plus 0.2, that's going to be 118.8. Do the same. This is going to be 119.0, and then 119.2. That's the fourth class. We only want 5 classes. 119.4. All right. So these are the lower classes. The lower bounds of each class. The upper bound will be 118.7. Notice this, that we go all the way to the accuracy, which in this case is to the tenths, and we subtract 1 from the next, and then 118.9, that's 0.1 less, 119.1, 119.3, 119.5. Notice it goes by 0.2. You know, this plus 0.2 plus 0.2 plus 0.2 plus 0.2 plus 0.2. That's how we get the upper limits. And then all we do is simply I'll count the frequencies. For example, in this case, all the observations that are 118.6 and to 118.7. Okay, let's look for all of them. So 118.6, I'm gonna highlight them. Another 118.6, and then another 118.6, and I think that's about it. Yes, 0.8, yeah, that's higher. So we have how many of them? 3. And then I'm going to use a different color to represent all the 118.8 and 118.9. So, okay, this is 1 right here. And then 0.9, 118.9, 118.9. Oh, there's 118.8 and 118.9. So how many do we have? 1, 2, 3, 4, 5, 6. So in this case, 6. Okay, let's go with the color. And let's do one more. Let's do another color. 119.0, 119.1, so 119.0, 119.0, 119.0, 119.0, 119.1, 119.0, 119.1, 119.1, 119.1. We have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. One more. Let's do the next one. Let me use green for that. So 119.2, 119.3. Okay, so 119.2, 119.3, 119.2, 119.3, 119.2. So that's 1, 2, 3, 4, 5. Total of 5 observations. All right, and that's supposed to be green. And no, I don't want to use blue, not pink either. That's another shade of pink, salmon, I guess, looks like. And 1.9, 119.4 and 119.5. So that's 1, 2, just 2. All right, just 2. And highlight with that color. And that's how we do an exercise like this. And this is all we have to cover for this chapter. I will see you in the next video.